Let x be a random variable on a probability space omega, f the sigma algebra on omega, and p the probability measure, with a density f acts as density f which is strictly positive on R. Let g be a strictly increasing differentiable function with limit at minus infinity of minus infinity, and on the other hand limit at plus infinity of plus infinity. And let y equals g of x, and h a non-negative function which integrates to 1 on the real line. And finally we let z here equal this combination of all the things that we just defined. So h of g of x multiplied by g dash of x, that's the derivative of g, all divided by f of x. That's of course another random variable. In part A, we need to prove that z is non-negative and it has expectation 1. So, by assumption, f, h, and g dash are all non-negative. G dash because g is strictly increasing. And therefore z is 2. So z is just a combination of these things. I'm not taking any negatives or anything, so it must also be non-negative. And that's not even almost surely, that's just a on every omega result. Further, the expectation of the random variable z, well, we could just plug this in, right? We should integrate over omega of the, so this is how it should look, z omega dp. Well, we could write z in terms of x. Get the brackets right, g dash x dp. And since x has a density f, this is by definition of that what it means to have a density. This is the integral now over the real line. I'm going to use y instead of x because it's clearer that it's a small letter. Of this, what was a random variable, but now that function applied to just the point of the space, times by the density of f, or density of x, which is f, integrated against the Lebesgue measure. That's what it means for f to be the density of x. Well, immediately we could cancel these f's, right? F is not equal to 0, so there's no problems here with dividing by 0 or anything like that. And now we can substitute gy equals, let's call this little z. And this, of course, is the purpose of taking g at minus infinity to be equal to minus infinity and at plus infinity to be equal to plus infinity, because when we substitute in, the limits of this integral don't change. And of course, by assumption, we assume this on h, that integral is equal to 1. Part B, we should show that Q, the measure which is defined on subsets of the sigma algebra as being equal to the integral over that subset of z against the probability measure. We want to show that Q is itself also a probability measure. So let's say let this define a measure on this measurable space sigma curly f. Okay, well, already it's given actually that Q is a measure. we just need to show then that it's a measure with total mass 1, and that will mean that it's a probability measure. Well, we see from part A that Q, the measure of the entire space, equal to the integral of Z against the probability measure P, is equal to 1. That's exactly what we showed, right? This is the expectation. Well, let's write that explicitly. That is the expectation of the random variable Z. It's just the definition of expectation, and we just showed that that's equal to 1. So Q is a probability measure. Part C. Now I want to show that the random variable y, which is given by g of x, has density h under this measure Q. Okay. Let sigma just be an arbitrary function from R to R measurable. That is measurable against the Borel sigma algebra on R. Since, as we, by definition of Q, we have that Q has density Z with respect to P, where Z is a random variable, but of course a random variable is nothing more than a measurable function from omega into the real line. So Q has density Z with respect to P. It follows that the integral over omega, although we don't really need to write this, usually that notation is omitted, the integral of sigma of y against dq is, by definition of Z as the density of Q, equal to the integral of sigma of y times Z against the probability measure P. Well, now we could just plug in the definition of Z and of y. So y, sorry, this is not y, but in fact, let's write it out explicitly. G of x, h of g of x, g dash of x over fx dp. But we can do exactly the same trick as before and write this using this is all now with the random variable x, of course. We can write it using the density of x. Exactly as we saw in part B. Or was it part A? I can't remember. Now an integral against the Lebesgue measure. So what was over omega is now over the real line. Once again, we get cancellation of f. Once again, we could do a substitution of g as we did before to see that this, sorry, that's not g now because the whole point is we do a substitution. So what we've shown, if we link the left-hand side and the right-hand side, is that for any measurable function sigma, this is true that integrating sigma of y against the probability measure q is equal to the integral over the real line of sigma multiplied by h against the Lebesgue measure. That is, by definition, under q, the random variable y has density h.